Hello students, today we are going to discuss some chemical properties of group 14 elements, comparison of properties of the oxides, hydroxides and halides, hydrides, their natures. So let us start from formation of oxides. Here if you see with the oxygen formation, with oxygen generally they produce oxides, that elements reacts with oxygen forming oxides. On heating with oxygen, generally at room temperature they do not react, but on heating in presence of oxygen they produce oxides. And these oxides, if you see, there are two types of oxides, MO2 and MO. Both produce monoxides and dioxides. But if you see that MO oxide, that MO, for example, generally carbon monoxide is produced. It is neutral. Carbon monoxide is neutral. And the structure of carbon monoxide, if you see like this is the structure of carbon monoxides. Then this carbon dioxide, if you see the structure of dioxides, that generally carbon dioxide structure is linear structures. This is the linear structure of carbon dioxide, and it has also resonance. Structure is, if you see the resonance structure, you can do write down like this. This residues O plus triple bond, C single bond O minus, like this structure. This is the structure of carbon dioxides. But the SO2, silicon dioxide is solid. It is solid, but carbon dioxide is gas. It is gas. Because it is a linear structure, but silicon dioxide, as silicon large size, it cannot form pi bond. This type, but rather it forms sigma bond, and it exists in this form. Silicon dioxide polymeric structure, like this. Oxygen will be here, then here oxygen, silicon, that oxygen, silicon, like this. This is the structure of silicon dioxide, SR2, in solid state. It is polymeric form. As it is in polymeric state, polymeric form of silicon dioxide, because silicon cannot form pi bond due to large size. The pi bond between silicon and oxygen is very weak. It does not exist. Rather it forms what? Polymeric silicon dioxide and exists in solid state. This is a very important question, why CO2 is gas and SiO2 is solid. But if you see the acidic nature, acidic nature generally carbon dioxide is more than SiO2, more than GO2, SiO2 than PDO2. Generally, these almost all are acidic. These are acidic, and this is your amphotericity. Silicon dioxide, because if you see the reaction, CO2 reacts with base, forming sodium carbonate and water. and your tin SnO2 reacts with base forming sodium stannate and water, and same SnO2 reacts with hydrochloric acid forming SnCl2 plus water. So both amphoteric character reacts with base, reacts with acid. So this is the nature of oxides of oxides of this group elements, carbon dioxide to PbO2. And this is the acidic character. Acidic character of carbon dioxide is maximum. Then PbO2 it shows amphoteric character. Tin also amphoteric character. So this is regarding the formation of the CO2. CO2 also reacts with ammonia on heating, NH3 on heating forming urea. It is also reaction of acid-base reactions. And this silicon dioxide is very important. Silicon dioxide reacts with HF, hydrofluoric acid, produce H2SiF6. That means that HF cannot be stored in HF. HF cannot be stored in glass vessel. In glass vessel, HF cannot be stored because it reacts with silica, glass, forming H2SiF6. Fluorosilicic acid, H2SiF6. So we cannot store HF, hydrofluoric acid. It is a liquid. We cannot store HF in where? In glass. So these are very important that properties of oxides of these group elements. Then next is with water. With water generally your carbon and silicon, germanium, generally carbon, silicon, germanium, tin reacts, carbon, silicon, germanium, these two very low reactive towards water. But your tin reacts with water on heating, produce SO2 and hydrogen gas is produced. Pb plus water on heating, very strong heating, produce PbO2 plus hydrogen. But what happens? A very stable oxide layer. That's why lead do not react with, generally do not react with water. This reaction takes place. This once oxide layer is produced, it do not react. That's why very stable to water. Stable to water. Due to formation of this stable oxide layer, reactivity is very low. And carbon, silicon, germanium generally they are very inert to the water. But a very strong heating, carbon and water, very strong heating, and you use steam. It produces carbon monoxide and hydrogen. This is called water gas or steam gas. This is called water gas or steam gas. So this is the reactivity of elements with water. Then formation of halides. Generally two types of halides produced, MX2 and MX4. There are two types of halides produced. And the stability of halides, suppose taking chlorine, carbon tetrachloride is more stable than silicon tetrachloride more stable than germanium tetrachloride. Germanium tetrachloride more stable than tin tetrachloride, more stable than Ap tetrachloride. So stability decreases. For the tetrahalide, the stability decreases. If you taking the same carbon atom, CF4 is more stable than CCl4, more stable than CBr4, more stable than CI4 on the basis of what? As chlorine is more electronegative, it can produce carbon C4 plus. C4 plus can be possible because chlorine is more better, stronger oxidizing agent. Because as very stronger oxidizing agent, it can oxidize carbon to 4 plus. So it is possible. But taking 4 iodine, the formation is not possible. This CI4 is not possible. That's why it is very unstable. So by increasing the size, the stability also decreases, and increasing halogen also stability decreases. So this is regarding. And another thing is important, carbon tetrachloride, these tetrahalides will water no reactions. It does not react with water because absence of vacant d orbital. It cannot accept lone pair from carbon. But silicon tetrachloride with water forming what? SiOH whole 4, SiOH whole 4, silicon tetrahydroxides, SiOH whole 4 and Sa. So formation of this one, that silicic acid, SiOH whole 4, hydrosilicic acid, SiOH whole 4. This is produced because it has vacant d orbital. It accepts lone pair from oxygen. When silicon having vacant d orbital accept lone pair from water, that's why it produces SiOH whole 4. So this is an important difference between carbon tetrachloride and silicon tetrachloride. Carbon tetrachloride is not easily hydrolyzed because due to absence of vacant d orbital, but silicon can be easily hydrolyzed due to presence of availability of vacant d orbital. Then if you see the stability of dichloride, if you see that CX2 is very less stable, SiX2, then GX2, then SnX2, then PbX2. Generally this is possible due to inert pair effect. Due to inert pair effect, I already know lower valency is more stable. That is possible. These three not possible. This is the stability. Stability increases, but that's why first three do not exist. Not possible due to that divalent of carbon is very unstable. So this is the very important concept of halides regarding halides and tetrahalides. If you and it is also very important. This silicon tetrahalides reacts with HF forming what? Si or AH2 SiF6. It produces due to formation of complex. Complex is formed because silicon has vacant d orbital. It accepts F minus. That's why it is possible. But your carbon CF2 plus HF, no reactions because it has no vacant d orbital. It cannot accept F minus from carbon. That's why silicon due to vacant orbital accept. That's why silicon produce higher covalency and produce complex, we can say, but carbon cannot show higher covalency due to absence of vacant d orbital. This is regarding halides of these group 14 elements and their stability, and which halides is easily hydrolyzed, which halides cannot be hydrolyzed. And if you see the complex formation generally observed in case of silicon. The silicon exists in Si, F4, Si, F5 minus, Si, F62 minus is possible. This complex is possible. Silicon also produce SiOH whole 6, 2 minus, like this. This type of complex is possible in case of silicon because silicon has vacant d orbital. So higher covalence is possible in case of silicon, germanium, tin, also lead. And generally the stability of lead in +2 state is more stable due to inert pair effect, already we have discussed. So this is regarding some important properties of compounds of carbon, silicon, germanium, tin and lead, and their property comparison of their compounds. Which carbon monoxide is a neutral gas, carbon dioxide is a gas which is a linear structure, which has that resonance structure, and silicon dioxide is exists in solid form. It is a solid due to polymeric structure. It cannot exist in monomeric form, that is linear structure, because it cannot form strong pi bond with oxygen due to large size. So these are very important concepts. Here also already I have told you silicon dioxide and silica, we cannot store HF acid in glass because it reacts with silica forming H2SiFC. That's how we cannot store HF in glass. So these are some acids that for another thing, if you see some extra questions, oxides that PB exists to PbO, PbO2, Pb3O4 also exists. Pb3O4 also exists. This is Pb3O4 is called red oxides. This is called red oxides. Okay, and PbO2. This PbO2 acts as a very stronger oxidizing agent. PbO2. PbO2 very stronger oxidizing agent. Very stronger oxidizing agent because it will reduce to Pb2 plus, because Pb2 plus is highly stable compared to Pb4 plus. So these are some property comparison of group 14 elements and their chemical behavior and their difference in the nature of compounds. Okay, thank you all.